So you saw the RG flow when you just have temperature last time, which we derive somehow from the 1D case. So what I'm trying to do now is generalize to the case when I have a set of variables. I'm calling them K, which is supposed to make you think of like the reduced temperature. But we'll mostly look at an example where we have a temperature and a field, say for example. And what we're trying to do is derive scaling relationships from the singular part of the free energy. So what I wrote last time was something like this. And because the number of degrees of freedom, n prime, decreases with one step of the RG like this, means the reduced free energy is a scaling dimension minus d, or at least the singular part does. Free energy. Let me say, we could write it like this, K prime, for example. And what we want to do is derive critical exponents from basically this type of scaling relation, except, you know, the issue is there can be many, many elements in this set. You could have an Ising model with next, nearest neighbor interactions, next nearest neighbor interactions, next nearest neighbor interactions, fields, staggered fields, I don't know, three body interactions, 4 body interactions. And so the question is, which variables are important when you derive this type of scaling relation? So before we look at that any deeper, let me just generalize this discussion of the scaling dimension by talking about generally relevant, irrelevant, and marginal operators. So what we're doing is we're extending our basically our RG transformation. So what we wrote last time was we derived something that was like K prime is a general transformation of one variable, a reduced coupling or reduced temperature. Now we have a set of K, and again I'm including things like fields and so on. And so let's look at the sort of linearized RG equation like we did for the single variable case, which means that we're very near the fixed point. So you're very, very near the fixed point, and you're doing the RG recursion. And so since you're so close to the fixed point, you Taylor expand. So let's just generalize this Taylor expansion. And the starting point, or the starting Hamiltonian, let's call it that, the starting Hamiltonian is very near the fixed point. Starting in the sense that you're starting with a specific set of couplings, or a specific set of variables, and you're modifying these through the successive RG procedures. So I'm going to define, for one, I call it, well, maybe n's a bad choice, but whatever. For one coupling, so for the couplings of this Hamiltonian, I'm very close to the couplings directly at the fixed point, right? And the fixed point is starred with a small deviation, which defines delta K. And similarly, after the transformation, or after the RG step, so the prime variable n, which is part of this set, is just delta away from the fixed point. So that defines delta kn prime. Okay, I'll use these definitions now in the linearized RG relationship. So just like we did last time, let's do the Taylor expansion, but over the set of these variables. And right, so what I want to do is perform a step of this RG, so Kn prime. So my Taylor expansion will be, the value evaluated at the fixed point, so Kn. Right, so I'm starting from here. Now I need, because R of K star is just K star. Now I need the derivative, and so the multivariate version of that, just by definition of the Taylor expansion. And this has to be evaluated at the fixed point. And then I can write this in terms of delta K and M, plus higher order terms. Okay, so these are just the same linearized equations that I wrote last time. So last time I only had one because I only had one variable K. So I'm performing the same procedure, just generalizing it. And I can rewrite this. Let me do it. Kn minus. Okay, I've evaluated R Kn at the fixed point. Let me bring it to the left-hand side. This is actually, by definition, delta K n prime. Basically, the deviation of that single variable from the fixed point value. And let me define this matrix element as just Tmn. Okay, just Tmn evaluated at the fixed point. And I've just written out delta Kn. And again, this distance has to be small in order to justify this Taylor expansion. So that defines. Okay, so that just defines what that matrix T is. Okay, so let's look more at that matrix. That matrix is a set of eigenvalues and eigenvectors. Let me label them with a subscript or a superscript. Well, my M's are already subscripts, so I'll use a superscript here. So lambda is the eigenvalues and the eigenvectors. I'll call them, I guess, eigenvector. So that, by what I mean is, if I have a sum over Tnm, then I have this eigenvalue equation, e to the I n. So from these, we define what we call the scaling variables. So generally in these RG flow diagrams, So in the one-dimensional case, we just had K, which was easy to relate to the inverse temperature. But generally, this, the variables that you describe the RG flows are made of linear combinations of the sort of bare couplings or the bare variables K. So the eigenvectors define that. So we just define the linear transformation, give us a scaling variable. Okay, we'll call them U. That's the eigenvector, that's the distance from the fixed point. Okay, then what we can do is relate the scaling variables using the eigenequation over there to the scaling dimension of the various K. So let me perform one RG step. It just means replacing K with K prime. Okay, just replace K with K prime. But now let me use, let's see, this relationship here, which is just a linearized RG equation. So I have to add a sum, NM. EIN. Now I have that matrix, PNM. And what I've done is I've replaced the prime with the unprimed M. Okay, but I know, okay, so I have a definition of a scaling variable, so I actually know how to relate this to the eigenvalue. So then I just have sum of M, eigenvalue, eigenvector, M, Km minus Km star, which is just the scaling variable, right? So I just have the eigenvalue and the scaling variable. So what I've done is I've just made a linear combination. So that imagine, you have a sum over n, so it could be, one of these n's could be temperature or inverse temperature, reduced temperature, whatever you want to call it. One of them could be reduced field. So all I've done is I've taken, say, my, t and h axis, and I've done a linear combination to, rotate these axes according to the eigenvectors of that linear transformation, the linearized RG equation. From that, I see how, the scaling variables, which are these linear combinations, these new axes, depend on the eigenvalues of that matrix. And so that defines the scaling dimension. If I just call this thing b to the y. Okay. So b to the y, and we have to have different scaling dimensions. I might have called this x before, but it's called y in the literature. So I have to have different ones for every I. So I can just call this byi ui. And that defines the scaling dimension for that variable. Okay, so this is basically as general as it gets. It looks a little messy because you have to have this sort of set of linearized equations when you do the Taylor expansion. But otherwise, it's exactly what we did last time with one variable. If you only have one element of the sum, then the linear combination's trivial. That's why the RG axis, only had one, it's one-dimensional last time. It's very simple. So the point is that, you basically have linear combinations of different physical parameters in your Hamiltonian, which define the scaling variables along which the RG flows are mapped out. Okay, so yi's. So I'll say this defines yi's. So these yi's tell you something important. They tell you what's relevant and what's irrelevant. So remember, last time I had a one-dimensional flow, which I sort of argued for in two dimensions, which had a 0 temperature fixed point, had an infinite temperature fixed point, had a TC, and temperature. Okay, and these were stable. I argued that these were stable fixed points. And I drew this RG flow diagram. This is the 1D. There's only one K. K is 1 over T. So the point is that temperature is a relevant variable from the perspective of this fixed point. If I perform this RG transformation, okay, very near to this, so it's like I perturb myself away from being exactly at TC, that's what this means, but I'm still very close to it. And then I start rescaling, renormalizing and rescaling. What happens? It's just like that video I showed you, right? When you're 1.03, TC, you renormalize to this infinite temperature fixed point. And if you're slightly below TC, if you've perturbed yourself below TC, you renormalize to this fixed point. So that variable is relevant when the temperature is relevant when you're sitting directly at TC. And how do you know it's relevant? It's because when you perform successive RG steps, you basically you drive that temperature either lower or higher. And the point is, not all variables in the Hamiltonian are relevant. When you start adding fields and next nearest neighbor couplings and next nearest neighbor couplings and dipolar interactions and everything else, you start getting a multi-dimensional RG space, and you think, well, how can you ever, you must have different exponents that depend on all these different couplings. But the point of universality and the point of, I think, the renormalization group is not all of these variables are relevant, and actually very few of them turn out to be physically relevant. Most turn out to be variables like temperature when you're at these types of fixed points. If you perturb yourself away, you just flow right back to that fixed point. Same with here. So temperature is irrelevant with respect to these fixed points. It doesn't matter if you're at T equal, in two-dimensional Ising model, the phase, if you perturb yourself away from 0 temperature, is the same phase. It's still a ferromagnet, right? So that idea of relevance versus irrelevance translates into all these sort of generalized set of variables. So there's 3 cases which you can, just by defining the scaling dimension, the scaling variable y, which you can distinguish.
Can I ask about the order of index of T? In the defining equation, there's T and N, and here T and N. So are they correct?
No, yeah, I probably just, I don't think it matters. Let's see, is T diagonal? I mean, symmetric?
Is it symmetric?
I don't see why not.
So that is the
yeah, so it doesn't matter. I could have, that's M. What I just write it as NM. I just switched this by accident. Any other issues?
I don't know, maybe you covered it last time, but I don't really understand what's happening here. So you take a point which is close to a fixed point, and then you transform it a little bit.
Right.
And you got a key prime, right? Right here. Yeah,
so last time, just write it real quick. So for one variable, you're writing the Taylor expansion like this. So we're just doing the same thing now. And the point is that near the fixed point, you know, R of K star is K star because the renormalization quits going. This is your derivatives, right? That turns into the derivatives there. And this is the distance. So this turns into your T matrix in the general case.
Oh, I see.
So that's just your Taylor expansion, yeah. So this is just, like I say, the generalization of that. And you know, in the last time we defined B of Y, and now we're just generalizing to have different yi's, and the i's tell you which scaling variable we're talking about. This will make more sense when you practice it on the assignment. So there's three cases which are important. If y is greater than 0, okay, then it's like lambda I, which is byi, so yi is greater than 0. Repeated RG iterations drive the u away. That means it's relevant. Say u and so if it's less than 0, when you have more and more iterations, ui just iterates to 0. If you start close enough to the fixed point. There's also the case where the y's can be 0, which is called marginal. Which means it's not so easy. You basically need higher order terms to tell you what's going on. Higher order terms in the Taylor expansion. I don't think we'll deal with marginal relevance in this class too much. So, as an example, so on your assignment question, so in your assignment question 4, you'll do the 1D Ising model with a magnetic field. So in that case, you'll have two variables. You have K and H, which are both reduced. So the beta is absorbed into them. So K is like 1 over T, or J over T. And H is like the magnetic field over T. So then when you perform the RG transformation, you get, in this case, you can exactly solve in part A for the RG recursion steps. And then I'm asking you to linearize them, which is basically this procedure, but you could also just expand out those equations for x prime and y prime. So from that, you'll look at the relevance or irrelevance of the two scaling variables, which are defined there for you. And you'll plot a two-dimensional RG flow diagram. So I can give you an example for another case, which is a little bit more complicated than what you're doing on the assignment. That's a case of Ising model with nearest neighbor and next nearest neighbor interactions. You just call it K1, say. Oh man. So it's called nearest neighbor. That just means nearest neighbor, that means next nearest neighbor. Oops, IJ. I'm not gonna actually do this. I'll just show you what the. Okay, so you form U1 and U2, which are linear combinations of K1 and K2. And then you can plot the RG flow diagram in terms of U1 and U2. Then you could transform it back to K1 and K2 if you want. Oops, K1 and K2. So let me just draw it in this physical parameter space to show you what things look like. So the RG flows for this model. So if you just had K1, which is the nearest two, this is 2D. Then you would have the same pictures I drew right there. Oh, sorry, that was 2D, not 1D. That's 2D, one variable. D is a spatial dimension here. So you have this on the axis. So you have two trivial fixed points. One's at K1 equals infinity. And so what you find is, so the question is, if you perturb, say, these fixed points with K2, is it relevant or irrelevant? So if you did this procedure on this next nearest neighbor Ising model, you'd find flow diagrams that look like this. Okay, so this is TC for the nearest neighbor. There's also a TC for the next nearest neighbor model, which is here. This flow is irrelevant. K2 is irrelevant at this fixed point. So these bent curves would be the transformed like U1 and U2. So you have a critical fixed point here with flows that look like this. You're basically flows look like this out here. And let's see, this one's got to be attractive. Okay, so you have a non-trivial fixed point here. You have a non-trivial fixed point here. You'll find that you have one here. It's a critical fixed point. They call this a basin of attraction. So if you're along this line, you flow into this non-trivial fixed point. And if you're off this line, you'll flow to something like a trivial fixed point, either infinite temperature, zero temperature, And so what all these lines are is different Hamiltonians. Right? It's like different, if K2 is 0 and you're sitting here, that's a different Hamiltonian in the reduced sense because the couplings are reduced than if you're out here. So if you're up here, then you have a K1 and K2 and a temperature. You can ask, what is the phase that I'm in? And all you have to do is know where you are with regard to these sort of critical, these basins of attraction. So if you're, say, tuning a temperature, in some sense you'll cut through this line with different trajectories, but this line will always describe, your critical point. Is always described by a critical fixed point. And the physics of that fixed point is completely determined by the critical exponents, which is what we're calculating now in terms of the yi. Okay, so different fixed points, 1, 2, 3, here, out at infinity. They basically have different critical exponents depending on what the various yi's are.
Where's the top right line flow to? Does it flow to K1?
Up here?
Yeah, does it move down?
I think there's one trivial fixed point out here. That's the infinite temperature one. So if I drew this in terms of u's, that's actually, there's no t equals infinity on here because you have to go to infinity. But if you write it in terms of u's, it's usually between u is 0 and 1 or something like that. So when you do your assignment, I forget what I asked, but if you draw it first in terms of u, you'll see that there's only one trivial fixed point at infinite temperature, and that gets smeared out to this big infinity out when you're in terms of the physical variables. So what I want to do is talk about how to relate the critical exponents to these yi's now. And we're going to do that through scaling of the free energy. So with that equation up top there. So now I have a set of k's. But I'm only going to care about the relevant operators. Okay, so if I'm at a fixed point and something's irrelevant, it basically means that scaling variable u doesn't affect the critical exponents. Relevant variables don't matter in that sense. Although I'm going to confuse you by the end of class about that. So, okay, so it's back to this. So the singular part of the free energy. Okay, and I want to write the exponents in terms of scaling variables. So I'm going to ignore, for now, irrelevant variables. And I haven't told you, for any fixed point, you basically have to, it's not a priori obvious what's relevant or irrelevant. You have to find the sign of y. But let's just do the simple case and assume just two relevant variables. I'm not going to do this example. I'm going to do kind of like the one on your assignment, which is temperature. And temperature is natural. And I think the lowest order field that couples to the order parameter is natural. So T and H. But let me write them in terms of scaling variables. So I'll call them UT and UH. And you're thinking of a reduced temperature and a reduced field, which measure the distance from criticality. Okay, so I'm going to write things generally in terms of U's, but by definition, reduced temperature, reduced field, near the critical point. Let me just simplify this linear combination that I wrote at top here, just near the fixed point, such that I'll just assume U is proportional to T. So it's got to be proportional, so let me just put a constant here. So I'm assuming somehow that the higher order, or that the linear combination gives you terms that are only higher order in the other variable. And similar for h. So I'm just defining h naught plus higher order also near the critical point. Yeah. Okay, so it's these like 3 boards or 4 boards are very general. I'm just making assumptions here that are relevant for the physical case. So let me write the free energy, which I've written as over that set of all couplings. Now I'm just going to write it in terms of these scaling variables. Okay, so b to the minus d, that's the scaling dimension of the free energy, or the free energy density. And, right, so b, y, ui is ui prime, right? So when I've done one RG step, what I'm writing here is b, there's 2 of them, and b, y, h, u, h. Okay, so I've done one trans. I was, this is the same as saying f prime is equal to b to the d f after one RG step. This is my prime here, right? I'm saying the free energy is the same up to this scaling factor, and a redefinition of your variables after one RG step to the primed values, which by that are given by this. Okay? And remember, this just comes from the fact that the number of degrees of freedom scale after one RG step is n prime b to the minus dn. So it's all back to very simple normalization. And we're just keeping track of it in the multivariable case. By the way, for you numerical aficionados, what we're working towards is a derivation of the finite size scaling forms from the scaling theory. So if this seems abstract, it's not. It's actually very concrete. Okay, so that's one RG step. Okay, so if I do n iterations, then this equation just times n. Okay, so in order to get this critical exponents, what I do is I assume I'm doing n iterations and that n is fixed somehow. Okay, so this is just a framework for deriving this stuff, but I need to stop my RG at some point. I'm very close already to the fixed point. I do a very large number of iterations, and then I stop. Okay. And again, remember the point is that the critical exponents are related to basically the R prime, the derivative of the RG transformation. And so all you have to do is enough steps in this linearized approach to sort of iterate out that behavior. So we're not specifying what that is. But then B, N, Y, T, U. So this thing, this coupling, which is becoming renormalized, or this variable, I'm just going to call K. for no reason. I'm just going to say that that thing's a constant. Okay, so that's maybe not obvious, but what that gives us is B. I think that's the only non-obvious step. Bn, written in terms of this constant essentially, and this is like T, your reduced temperature, and that's your scaling variable or your scaling dimension. So then the free energy will be, okay, what is this? U, so I'm going to do 1 over that, over K, D over YT, my free energy. That argument is just fixed, KT, but here I have that fixed number, YH, YT, and UH.
You fix it, or you fix it to be constant, or?
Yeah, because I'm fixing n. N's large, but finite. It's just an assumption you have to make on n. It's basically saying that n's not infinity.
But like if you make another step, rho KT.
Well, you're looking at sort of the asymptotics. So things are changing. You're not exactly at the fixed one. You perturb yourself away. So you perturb yourself away a finite amount, and then you run a huge, large number of n back. And what you're asking is how does, what can I calculate from that procedure of running myself back without actually taking that procedure to infinity? Because it's like you can do n infinite amount of times and still not be at the fixed point. It's like Zeno's paradox. So you just fix it. And again, the important thing is, like just as a note, what I said last time was somehow the, by's, when I did one variable, by's were related to r prime k star. And we've linearized everything. So we're trying to figure out, how y's affect critical exponents. And we don't maybe explicitly have this derivative, right? We only have the linearized form. So the content of the RG is in the transformation itself. That's the point. Is like the information that we're gleaning is from the procedure. Okay, so that's your free energy after a whole bunch of steps, fixed number of steps. And that's it. All I want to do is get rid of that KT. It's just, just absorb it into the definition of, this would look way simpler if I just used U equals T and U equals H and forgot about those constants. And you could redo these few steps like that and you'll see how simple it looks. We already have a constant, no sense having two. So the general way you'll see this written, U's are just dependent on the variables in this case. It's the physical variables. I have T over T naught, D over Y. That's my free energy. The function on the left-hand side you can write as free energy, but often you just write it as a scaling function, which is called big phi. KT is a constant, so we don't care about that dependence. What I have is dependence here, H over H naught. And then I just have T over T naught on the bottom. And it's YH. I think this is right over YT. And this scaling function, which I've just called phi, is universal. So it depends on these variables in this manner. But if you scale the x-axis with, if you plot it versus this, then that function phi will be universal with this amplitude. So from that free energy now, I can derive the critical exponents. Because all the critical exponents are is relating physical variables to the divergence which is occurring out front of this scaling function. Okay, so for example, for the magnetization, we know, now let's do specific heat first. So specific heat, I can set H to 0, because there's no, it's not a response to H, it's a response to T. So, space. So set H equal to 0, second derivative of the free energy with respect to temperature squared, but H equals 0, I can say. This is T to the, we know that this gives us alpha, right? So it should be equal to the reduced temperature to the alpha. That's how we defined the critical exponent alpha. So all I got to do is take a derivative of my free energy with respect to temperature twice, and now I can relate alpha to the scaling dimensions y. So second derivative of that singular part of the free energy. So forget the scaling function, all I care about is the singular behavior. So you already have T out front, so it's just two derivatives. That's all it is, so let's see, there's probably a minus sign, so alpha is 2 minus d over yt. So if you can solve that set of linear equations, if you can get the scaling dimensions, then you get the critical exponent. And you can just read them all off like this. What's the next one? Let's do the magnetization. This one you need to leave in the field because it's a derivative of f with respect to h. Then you set h equal to 0. How does this work? It's m. M goes as t to the beta, right? So from that, let's see, it's a single derivative. So I'll just say it's t to the, so you have an argument. Okay, so you take a derivative with respect to h, use the chain rule. So this factor comes out front. You already have a t over t naught. So that just means you have d minus y h over yt. Susceptibility, it's a second derivative. So you take another derivative. And set h equal to 0. So that'll give us something that's d minus 2 yh over yt. that defines gamma, remember? So gamma is minus this. And the delta, the critical isotherm, I'll let you do that one on the assignment. Do I give it to you there? It should be like question 2 or 3 in terms of y and h and yt. Okay, so I won't write it down. So it all comes from the free energy expression. Okay, so we have relevant variables. They have scaling dimensions. They give us critical exponents. And you see that the critical exponents are all related to, in this case, just 2 variables. We have 2 relevant variables in this case. You just eliminate y, h, and yt to get the scaling relations. These are called the thermodynamic scaling relations sometimes. That's the one without delta, and the one with delta, so you need to do delta from your assignment to get this one. These are essentially, so you just solve that system of 4 equations to get these. So they're related. These relations were actually postulated before the RG came along. So before the scaling hypothesis, people basically observed this, so they knew that these were obeyed. But the reason they were obeyed is basically because of this form of the free energy here, which comes from just considering the RG procedure. So very abstract, gives you, something very concrete, and just a very few steps in manipulation. I think you just have to make the proper assumptions. You perturb yourself away from the fixed point, some very small amount. Then you do a fixed number of iterations back and just look how things scale. So you're just controlling the RG iteration procedure by making sure that you're not too far away and there's no infinities in your calculation, and you get these scaling relationships out. And that's how you calculate critical exponents. So if you want to know whatever beta is, you just basically do this procedure of diagonalizing that T matrix. Okay, so these are the easy ones. There's also critical exponents. I think the only hard one, maybe besides delta here, is the relationship between the scaling dimensions and the critical exponents for 2-point correlation function. So let's just look at that real briefly. Any questions on this?
If you go back to the diagram, right?
Yeah.
So RG tells you how the things behave very closely to critical points.
Well, it tells you basically what phase you're in, no matter where you are on that diagram.
Why no matter where you are?
Because if you're far away, if you do the procedure exactly like you do in 1D on your assignment, then you see how, even if you're far away from the fixed point, you just see how you iterate towards, the fixed point describes a phase that you're in. So even if you're here, which is far away from the fixed points, if you apply the RG procedure enough, you'll flow to this Hamiltonian. That Hamiltonian means that coupling. That's the K coupling for t equals 0. It's the fixed point Hamiltonian. So if that's what these arrows mean. If you apply enough RG transformations, you flow to this Hamiltonian. And the long wavelength degrees of freedom, because what you're doing is you're looking at longer and longer length scales, are described by that Hamiltonian. So the idea is, even if you're way out here and you have a lot of microscopic details that make it unclear maybe what phase you're in, this tells you which details are relevant and which details are irrelevant in terms of a long wavelength description of the phase. So even if you're way up here and you start performing the RG procedure, you'll go along some trajectory that moves you into here. If you're here, very close to this fixed point, and you do this long enough RG iterations, you'll flow all the way back here. Which tells you that Hamiltonian, whatever that is, maybe it's something that's only slightly away in temperature from the critical point. It tells you the physics at long length scales is not described by the critical model, it's described by the trivial model at t equals 0. It tells you this is ordered, it tells you this is disordered, and it tells you if you're sitting here that that's at a critical point. So you don't need, like, this derivation, everything I said after this, assumes that you're near the fixed point and you're iterating back, but that's just to get the critical exponents, because the critical exponents are just describing the behavior, asymptotically close to the fixed point. Does that make sense? And the other point is that universality comes from this picture, because remember at the start of class we were trying to understand the sort of mystery of universality. What this is telling you is that there's only a certain number of variables that are relevant. So you can have all these other microscopic next nearest neighbor, next nearest neighbor, and many of these which make up this huge Hamiltonian space are irrelevant. So the physics of the critical point, like this critical point, is described by a very simple theory that only has to do with the relevant variables, like in this case t and h. Everything else at that fixed point that you might see in microscopic real Hamiltonians doesn't contribute to these relationships here, because these only depend on the scaling dimensions of the relevant variables. So the irrelevance is basically what gives you universality. So, relevance and irrelevance are responsible for universality. That's the point of the class. We could just stop here for the whole semester. So it's really that basin of attraction that I drew in the middle, that critical fixed point in the middle, which is a new fixed point. There's a basin of attraction that you flow into it because variables are irrelevant. So there's only just a very small number that tell you what the critical exponents are of your system.
How do you know how to connect those basins of attractions? Like, maybe there is another way to,
Well, there's a huge higher dimensional space, all your couplings. There's only one relevant direction here. And, if you do this procedure for a complicated Hamiltonian, what you find typically is most variables are irrelevant. So I haven't told you why. That's something we'll see more of when we do the momentum shell RG. So if you have the phi-4 theory and you do phi-6, phi-8, phi, whatever's 8 plus 2 is, you basically see that the couplings in front of those higher order, higher powers of phi are irrelevant variables. So you can prove that in like an Ising model, you only have 2 relevant variables. But we can't do that for another month.
Well, given you have only 2 relevant variables, and you put those 4 critical points on the plot, right? And then you know what the flow in the neighborhood. What guarantees you that you cannot connect them in some other way? Maybe the TC on the horizontal line, maybe by the length flow to the vertical line TC. Like
You don't know. I mean, you have to do that. In that case, you have to do that calculation like you're going to do in question 4. So when you do a question 4 in your assignment, you'll see the structure of the fixed points there. So first thing you'll find is the fixed points. You'll say, okay, there's, in that case, 1, 2, 3, 4, maybe 5 if you count infinite temperature. So you see there's 5 fixed points, okay? And then the question is, you put those 5 fixed points on your U, with all your U axes, and then you start looking at those 5 and you iterate away, and you see, if I do this iteration, am I flowing away or am I flowing towards them? So first you find the fixed points, then you look at the space around the fixed points, which is basically exactly what you're doing on question 4. It's almost like I know what I'm doing, but really it's completely random. Again, this is really abstract. This is just the framework. You'll never understand it unless you do examples. And I think that's what the point of the assignments is. So, okay, what do I want to do? I think I want to confuse you now. And the reason is physics is confusing. So there's special cases. Okay, this describes almost everything you'll encounter in real life. But there's special cases where irrelevance matters. And it's in the 2-point correlation function, unfortunately, where confusion raises its head. So 2-point correlation function, that's to define the correlation length. Actually, I can figure out the behavior of the correlation length. We've already derived it in the case of one variable, the exponent nu. It doesn't occur here, right? So let's look at the exponent nu first. That one's not confusing. Instead of the free energy, let me just write the correlation length, UT, assume that there's a UH. Instead of b to the minus d, it's simply, so I'm replacing, basically that equation there. So it's basically just b for every iteration. So after many iterations, it's b to the n, correlation length, and everything in here is the same. H, UH. Okay, it's just a length scale. So every time you do an RG step, you pick up a scale factor, right? That's n RG steps, fix n. So the correlation length, once you start from that form, gives you a very simple relationship between y. So let me just pull out. Okay, so it's b to the n. I know what b to the n is. I just wrote it up there. It's kt over ut 1 over yt. That's basically it for the correlation length. Oops. And same thing, absorb this constant into the constant that's in here. So I have 1 over t is 1 over yt. And I know the correlation length goes as t to the minus nu. Okay, so I can just say, we already derived this, nu is 1 over y. That's when I only had one variable, and that was the variable associated with t, or k, if you will. And so here it's just the same. There's no additional dependence of y, h in the 2-variable case on nu. Okay, so that's nice. Correlation length's not so, the correlation function's not so nice. The correlation function, remember the 2-point correlation function depends on spin variable sigma. I haven't derived the scaling dimension for sigma yet. So just recall we call it x. If it's a prime on the left, it's b to the x a. That's a scaling dimension x. So I want to know the scaling dimension of the 2-point correlation function, but I need to know the scaling dimension of sigma, the microscopic variable. So let me just call it x for now. So let me say sigma. Another way to write that would be, with my rescaled index for single sigma I. Or I could also say that there's a R vector, Ri, associated with I, right? Because my 2-point correlation function, G, I'll say Gij. Now there's 2 indices. Let me assume that it's just Ri minus Rj. Just depends on the distance, which I'll call R. Just a I, J, R. So the scaling dimension matters here because, it's this minus this. So if that's a scaling dimension for a single microscopic spin, then I expect 2 things: a magnetization to have a scaling dimension. How do I want to write this? The same scaling dimension. And for G then, say G of R, I'll just write it like this. G prime is G R. And you have to redefine that length scale. So maybe I should call it R prime. Okay, so after one step of renormalization, let me write this now in the same notation like I have over there with U's and so on. And then I can extend this to the case of many steps. So let me write in terms of R, T, and I think I want H equals 0. Yes, I do. So I'm just going to write in terms of R of T. I'm inverting this, so it's b to the minus 2x. And this is my G prime. And I could do the same thing for M. There's no R anymore. T, H equals 0. So b to the minus x. Oops, P over T naught. Okay. But if I look back at my free energy after one iteration, I have it written up here. Oh, that's n iterations. I can also calculate m in terms of one iteration here. So let me just replace n with 1. Right, so if I look at that, then if I take the derivative, which is mt, then I get b to the minus d, what, b to the y h, 1 over h naught from here, right, because that's h over h naught. Then I'm doing chain rule, I guess, so I have the derivative with respect to h of f, s here, byt, t over t naught 0, and that's just the magnetization. So that's a different equation. I have an equation for this. I'm defining the scaling dimension here, but I'm also relating that scaling dimension to these two quantities, yh and the dimension. That's it. So I'll call this I think it's b to the minus x. I've done it right, so that's, yeah, b to the minus x equals b to the minus d plus yh. So x should be so that's a scaling dimension of the microscopic variable. It's a scaling dimension of the spin, it's a scaling dimension of the magnetization. In terms of the dimension at h. So it depends on the scaling dimension of the field, because that's a field that couples directly to the order parameter. That's why we use the field here. If you had a different order parameter, you'd use a different field, basically. Okay, so that x, I can just plug in to get the scaling dimension for the correlation length. So you got a factor of 2 there. That's your G prime. We're going to come back to this next class. This is important in our definition of the anomalous dimension, which I'd like to get to. So this is only for once. This is n equals 1. Iterate to some fixed large n. Remember, it's b to the n, yt, ut. Which gives me a g. I pulled a 2 out, I think. So I have a minus n here, r. This form is going to be what gives us finite size scaling relationships, by the way. Okay, so I substitute in b to the n for this fixed K, and you should get, after one step, I'll just write some general scaling function. So this is interesting because we already know that away from the critical point, the correlation length's exponentially decaying. That's how you define the correlation length. The 2-point function has an exponential decay. So that exponential decay must be part of this phi function. And so the arguments here, RT to the 1 over y, are, which y is that? YT, right? Is related to that exponential decay. So we know that this is e to the minus r over xi. And we know that xi, okay, so that functional dependence here, t must be, correlation length must be t to the 1 over y. Well, the inverse of that. So that again gives us the fact that nu is equal to 1 over yt. So there's a prefactor here, but the exponential decay is what wins away from criticality. So next class, we're going to look at the 2-point correlation function directly when t equals 0. So we're going to go back to this equation here. I'm going to set t equals 0 here. Well, you can do it in your head. And so this is basically the scaling dimension at t equals 0. Okay. And it relates to b, but there's no length scale. There's no length scale at all in the problem past that r that's defined there. So it has to be r. So it's r to the minus 2d plus 2 over 2 times y. Okay, so we'll look at the case exactly at criticality, and that'll lead into our discussion of the anomalous dimension. The anomalous dimension, you're looking at it in question 1. It's anomalous because the dimensional analysis that you perform on Landau theory, like we did a couple classes ago, if you do it on the 2-point correlation function, you don't see any evidence that there's another exponent. So this exponent here, or this scaling dimension, there's no evidence that that's related to any non-trivial exponent that we haven't seen before. But what I'll tell you next time is basically the fact that if you're right at the critical point, this function can also have a divergence or a singularity. And what happens in physical systems is it just does. And it defines a new exponent that you basically have to multiply to this mess here. That's eta, that's the anomalous dimension. It's important in many modern theories of sort of composite bosons. If you have two fields phi that sort of, like if you have a physical field like a boson and it fractionalizes into two fields, then that fractionalization is manifest in the anomalous dimension always. Because the 2-point correlation function is sort of the physically relevant thing that you measure. So it's important to know it exists. You'll see it in your research. We won't calculate explicit cases of nu, except maybe when we go to like an O2 nonlinear sigma model late in the class. So I'm going to do that next time. And I'm going to do finite size scaling, and then we're going to start the momentum shell RG. Okay? Questions?
Yeah, I'm not sure whether something in the subscript ends or H's.
They're all H's.
Right.
But they look like N's. The only N that occurs is the number of fixed iterations here. Anything else? Bring me your assignments. 2 weeks till your next assignment's due, and then we'll take a week off to catch up on assignments.